Alright, so last time we were talking about some of the properties of gases. Today we're going to talk about how the pressure, temperature, and volume of a gas are related to each other. So the first law I want to talk about is Boyles Law. Boyle is the person who came up with the relationship between pressure and volume of a gas. And he said the pressure and volume of a gas are inversely related or inversely proportional. So if you keep the mass and the temperature constant, so if you keep them the same throughout the entire experiment, you will see that as pressure increases, the volume will decrease. And as pressure decreases, as it is here, the volume is increasing. So make sure you make a note of this graph, record it somewhere in your notes. And this shows an inverse relationship, but you can also see an inverse relationship if you were to flip these axes and just do a little bit more math. So let's say that I have pressure over here and volume over here. And then I take those values for pressure and I make them a fraction. I say 1 over that number. What I actually see is a graph that looks like this. If you ever see something like this, where you see volume, or where you see something right here, and then the other factor is 1 over a number, and you see a straight line going up, that's an inverse relationship right there. So this shows an inverse relationship. So make sure you make note of both of these graphs right here. So if you are looking at something, let's say that you're looking at the pistons in your car. So you know that in the engine, pistons go up and down. And right here, let's look at this piston. There's not that much pressure being exerted to this gas, and it has a lot of room in there. But if we start exerting more pressure, we're pushing all those molecules closer and closer together. So the volume is decreasing here. So this is where the volume is decreasing. You're just forcing them to be closer and closer together. So again, we increase the pressure some more, and then we're decreasing the volume even more. So as one goes up, the other one goes down. So I want you to write down the mathematical formula that Boyle came up for this, and later I'm going to show you just one formula to keep all of these formulas, keep track of all the formulas. So just write this down. I want you to be familiar with it just in case you see it. So the initial pressure times the initial volume. So whenever you see a 1 by a variable, that just means initial, is equal to the final pressure times the final volume. So this is the mathematical relationship that Boyle came up with for pressure and volume. And we will be using that, but probably next podcast. Alright, so Charles's law. Charles, this man right here, he came up with a relationship between volume and temperature. Now, it says absolute temperature here because the temperature has to be in Kelvin. If it's in Celsius, this will not work. So he said that the volume and the absolute temperature of a gas are directly related. So they're directly proportional. As long as you keep the mass and the pressure constant, you'll see that relationship. So make a note of that graph. So as the volume increases, the temperature also increases. And that makes sense. If you were to take a balloon and you were to heat it up, well, what happens is those particles, those gas particles, get more and more kinetic energy, and they start moving out more. So you would actually start to see the balloon expand. So let's take a look at that. let's say that we have a balloon right here. It's at room temperature, and then I decide to pour some really, really cold liquid nitrogen on it. So I'm decreasing the temperature here. If I decrease the temperature, the kinetic energy decreases and they start moving closer and closer together, those molecules. So the volume decreases here. So that's what it means when it says, okay, you have a direct relationship. So if you decrease the temperature, the molecules are moving a little bit slower and they're moving closer and closer together, so the volume shrinks. Now, Charles also came up with a mathematical relationship, so make note of that too. And he said the initial volume divided by the initial temperature of that gas is equal to the final volume divided by the final temperature of that gas. So again, just make a note of that. Alright, so Gay-Lussac came up with a law. And he came up with the relationship between pressure and absolute temperature of a gas. He said that they are directly related. So, as temperature increases, so does pressure. As temperature decreases, so does pressure. So as one goes up, the other one goes up. As one goes down, the other one goes down. And this is, again, at a constant mass and volume. Alright, so let's just take a look at two things right here. Let's say that you have an aerosol can, like this man right here. Inside that can, you have gas, okay? And if you increase the temperature of that aerosol can, and if you actually pick up an aerosol can and look at it, there will usually be a warning that says, do not, keep it at a certain temperature, or do not allow it to be in a hot temperature. That's because as you increase the temperature of that gas that's inside that can, the particles will start to have a higher kinetic energy, which means it's going to increase its number of collisions against the can, which means the pressure is higher. More collisions equals more pressure. So if you were to leave a can like this out in your car in the middle of summer, this could happen. So as the temperature increased, so did the pressure inside the can, and eventually it got so high that it exploded and the can went through the window shield. So that's definitely an example of Gay-Lussac's law right there. You can also see an example of Gay-Lussac's law if you pick up a can of, it's like an air duster. If you've ever seen these cans where it just squirts out air, like its whole purpose is to squirt out air. It's used to like dust computer parts and machines and things like that. Well, as you spray that air outside, you're decreasing the pressure inside the can because there are less molecules, there are less collisions. So that gas is being expended and you're decreasing the pressure. Well, if you've ever felt the gas coming out of that can, you'll see that it's cold. And it's cold because you're decreasing the pressure. If you decrease the pressure, you will also decrease the temperature. Alright, so let's look at his mathematical formula. And his formula is, if you take the initial pressure and divide it by the initial temperature, it is equal to the final pressure divided by the final temperature. So notice all of these laws are set up to figure out, okay, if you change of pressure, temperature, volume, what happens to the other thing? What is that number? What is that value? Alright, so through a lot of math and experimentation, Boyle said that you will get a constant, so you'll get the same number if you multiply the pressure of a gas and by its volume. Charles said you'll get a constant if you take the volume and divide it by the temperature. Gay-Lussac said if you take the pressure and divide it by the temperature, you're also going to get a constant. So if you take all of those things together, you're going to get a constant. They're able to derive an equation that looks like this. This is called the combined gas law. Okay, so the initial pressure multiplied by the initial volume divided by the initial temperature is equal to the final pressure times the final volume divided by the final temperature. I don't like working with this equation. That's why I always rewrite it to look like this. This is much easier to work with. So if you know this one equation right here, you know enough information to solve for any of the gas law problems. All right, so next podcast, we're going to actually go get into how to solve these problems, and I will see you in class.